Hello everyone, I'm Lara from eProsima, and today I will host this embedded working group. As a recap, at the last meeting, Antonio Cuadros from eProsima demonstrated an open manipulator X control approach by Renesas and eProsima using micro-ROS. Also, Daniel Salmen from Hanging Electrowork was here, and he talked about micro XRC EDDS as an interface for drives in AMRs. And for today, we have a presentation on eProsima's latest middleware solution, SafeDDS. Pablo Garrido will discuss the key features of this new embedded middleware, including its architecture and performance capability in terms of memory usage, CPU, and latency. Additionally, we'll highlight SafeDDS' most relevant functionalities that make it an ideal choice for safety-critical and embedded applications. So, Pablo, are you ready?
Yeah. Hello, everyone. Can you hear me well?
Yes.
Okay. So I'm going to share my screen.
Okay.
I
Perfect.
guess that now you should be seeing my slides. Okay. So hello, everyone. Nice to have you here because today we are presenting the latest middleware solution of eProsima. We have been working on that for the last 2 years and a half, and we are very proud to share with you here in the embedded working group this new product. Well, SafeDDS is the new product that we are releasing, and it is something in between of the two middlewares that you already know, FastDDS and XRCDDS. As you might know, FastDDS is our open source complete DDS solutions that targets general purpose systems, and XRCDDS, which is the base of the middleware of micros, is the embedded approach that we used to have in order to provide DDS APIs into highly embedded systems. And we found that we have a gap in the middle of both of them, because we found that it is possible to make an embedded DDS solution that provides almost the whole DDS API in embedded systems with limited resource usage, but without the bad things of XRCDDS, for example, having an agent. And this is why we have created SafeDDS. The main target of SafeDDS is the automotive sector. And this is why we target the certification in terms of safety, well, following the procedures of the ISO 26262. And this is our main target. But as I'm gonna explain in this presentation, SafeDDS is something more than this, because you can use it in multiple critical systems and some embedded systems, and the usage are very wide. In general, SafeDDS is a safety-certified DDS-compliant middleware library that targets mid-low range MCUs and CPUs. And of course, as we target the automotive electronics, we target ECUs, electronic control units, that are in cars, in all the automotive systems. And we target the ACLD, that is the highest certification level that ISO 26262 provides. In general, the main characteristics and the main difference between the FastDDS product that you already know and SafeDDS are that SafeDDS is written from scratch, following very strict code guidelines, such as MISRA C++ or AUTOSAR C++. And also it has 1% branch coverage, MCDC coverage. We follow this very strict methodologies and code guidelines in order to ensure the requirements that a safety system needs. We also have requirements and documentation for all the whole code base, and we we have requirements for every functionality that the library provides. We have used, as I have mentioned, we have written this from scratch. So we have used a C++ subset. We have an architecture that is based on interfaces. We have a very modular architecture that we are going to see in the next slides. And we use a C++ subset that means that we are not using the full feature, for example, C++ standard library, in order to be portable and in order to be able to integrate SafeDDS in a lot of different systems. In terms of modularity and portability, we have learned a lot from XCDDS and from Micros. And SafeDDS is a product that targets to be multi-platform. It has a flexible execution model, and it allows to have multiple transports, not only the classical UDP network transport, but also the transport that we are used to see in Micros, for example, serial ports or SPI or CAN buses, all these kind of different transport that we find in embedded systems. Regarding the memory control, this is another point where we have learned a lot from Micros, and we have designed SafeDDS to provide the user a full control over the memory that is being involved in the DDS procedures. We only use a stack and static memory. We provide modes where only stack and static memory are used, and where the user can configure the library to have no heap allocations. But of course, we also provide modes where dynamic allocations are allowed, but they are controlled. You have allocator controls over the allocation that the library needs to do, in the same way that you have in Micros, for example. If we compare SafeDDS with our eProsima's solutions, we can see that if we compare SafeDDS with XCDDS, we see that in SafeDDS we have a full compatible DDS API. We don't need an agent because, of course, DDS is a distributed data system, so we don't need a broker to broke or the data from the communication endpoints. And we also provide certification artifacts because this is a safety certified implementation. On the other hand, for example, we can say that XCDDS is still much small in terms of memory footprint than SafeDDS. We are going to see this in a next slide, but I can say that it is not so much bigger. SafeDDS is, you can compare SafeDDS more with XCDDS than with FastDDS. We are talking of a memory footprint of about tens of kilobytes instead of megabytes. If we compare SafeDDS with FastDDS, we have a lot of advantages. For example, SafeDDS is a very, very portable library, and it can be embedded in any kind of RTOS or even a bare metal system. We have a predictable operation and execution. The user have full control on the SafeDDS executor and on how the entities will behave and will perform the task that they need to do. In that sense, for example, we don't rely on a threaded model. We don't launch threads. Instead of that, we provide APIs for allowing the user to control the operation. We will see this in the architecture slides in the next moments. If we compare with FastDDS, we also have a much less memory footprint. In terms of performance, for example, if we talk about throughput or latency, we are in the same values. We have achieved a library that allows the user to have the same latencies and same throughputs that you can achieve with FastDDS. And also, of course, you will have available the certification artifacts. Of course, the perks of this library is that we don't have advanced DDS features. We don't have the complete support of the DDS standard because the DDS standard is huge. And for example, we don't have content filtering or advanced QoSs in SafeDDS. If we talk about the SafeDDS architecture, as I have mentioned, we have a modular architecture based on interfaces that provides these layers that you can see here. The most important one, of course, is the DDS layer. We can see in this slide. In the DDS layer, we provide a the DDS APIs that you may know from the usage of fast DDS, and you will find a normal DDS participant, DDS topic, subscriber, publishers, data readers, and data writers. For example, in terms of writing data to the DDS namespace, the safe DDS data writer only expose the write operation, and in terms of reading data, it only exposed by now in this version the taken examples. You won't be able to read an example. In that sense, we have reduced the DDS API in order to provide a solution that is useful for the DDS user, but also that allows to embed it in every kind of platforms. In terms of QoSs, you will find that Safe DDS has the most important ones. We have reliability, both reliable and BC4 modes. We have durability, both volatile and transient local modes. In terms of history, we have keep all and keep last and keep all, sorry. And for example, in terms of resource limit, of course, you will be able to configure the resource limits of the DDS entities in the same way that the DDS standard explains. But of course, you are not going to be able to use unlimited length, because we need to have control over the memory, and these kinds of QoSs are not compatible with our initial restrictions. And also you will find all the standardized DDS listeners, and you will be able to access to the liveliness of an instance in DDS, and also to handle deadlines of writers, readers, and all the behaviors that are expected from a DDS implementation. Well, as I have mentioned, we have a very, very, very isolated and modular and layered architecture, and behind DDS we have a couple of things. The most important things are protocol and data-centric. Protocol is a layer that exposes and implements a wide protocol. Here, the user will find concepts of a writer, reader, a catch change, reliability in terms of wide protocol, GITs, and messaging processors, and all the things that are related to the wide protocol. And of course, we provide an RTPS implementation. This is why we need to be compatible with other DDS vendors. So we need to provide an RTPS implementation. Below, we have the transport module, that is a layer that abstracts the library from the transport concepts. So here, the application user will find the concept of a message sender, message receiver, locators, and all the things that are related to transport. And here, for example, is where we can implement transport that are not only based on the classical Berkeley socket. So, for example, we have implemented transport for FreeRTOS plus TCP, Lightweight IP, and we have been experimenting with serial transport. Well, we can use the whole DDS stack on top of any transport that is able to send messages in the same way that micro-ROS transport works. Also, we have this data-centric namespace or module in between of protocol and DDS, because we found interesting, for example, to provide APIs that are not fully DDS compliant, but also that they provide this data-centric approach of a middleware. And for example, here in data-centric, you will find writers, readers, and all the entities that you need to communicate, but you won't have access to the DDS QoSs, or for example, you won't have access to types. In that sense, data-centric is type agnostic. Now that we have seen the main three layers, DDS, data-centric, and protocol, I can say that the user of the library will be able to choose at what level he or she wants to write the application, depending on the requirements and depending on the memory constraints that they have and all the things. But of course, we have also other support namespaces or support modules that allows us to use Safe DDS in the way that we have. In that sense, for example, the discovery module will abstract the discovery procedures. Of course, it provides an implementation of a simple entity discovery protocol and simple participant discovery protocol that are the mechanisms that the DDS standard requires DDS implementation to have in order to be interoperable with other vendors. But in that sense, the discovery module will allow a user to, for example, implement its own static discovery or another kind of discovery that relies on other kind of mechanisms that are not the common multicast DDS discovery. And here we have the supporting modules that are used along the whole stack. And for example, we have the memory namespace in order to have a safe operation in terms of the safety standard. In order to have a safe operation on top of the memory, we don't use like raw memory access in the whole DDS stack. We provide views on top of buffers that allows us to code the main stack with an abstraction on top of the raw memory. So this allows us to have a full control over where we have a memory view that can be modified, or a memory view that is constant, or a memory view that can be mutable, or an array of memory views, all those kind of things that are important to keep the whole code base safe. In terms of serialization, this namespace is very basic because we provide serialization and deserialization abstractions, and we provide a fully compliant CDR. In the same way that with discovery and protocol, we need CDR in order to be compatible with other vendors. And for example, now we have a very interesting module that is the execution module. Here is where we provide solutions for allowing the user to interact with safe DDS in non-common execution models. For example, we don't assume threads. In that sense, in the execution namespace, we define what is the spinnable interfaces of the stack. In that sense, you will find methods such as, for example, spinning war, or spin for a certain amount of time, or spin until this time point, or even spin but do not block. That is very important for a system where we need a non-blocking operation, and all the execution of the DDS stack is defined in the execution namespace. And finally, we have the last two namespaces that are portable and platform. Here we find very important solutions in order to make safe DDS portable and multi-platform and flexible in terms of embeddability and all those kinds of things that are important for working with embedded systems. In that sense, portable encapsulates all the features that are not language. We have developed safe DDS in C++ 14, but we don't have a direct usage of, for example, the STL. Instead of that, we have encapsulated the objects, the classes, and the functions that we use. In that sense, for example, we don't use directly std array. Instead of that, we have a portable array that can be implemented using std array. In fact, the default implementation that we provide is std array, but it can be changed to the implementation that the user needs. And it's very, very, very easy to modify any kind of concept that we have encapsulated in portable. For example, the classic libc methods, memcopy, memset, or those kind of memory methods are encapsulated in the portable namespace in order to allow the user to modify them if it is required by your toolchain, by your compiler, or by your version of libc. And finally, in terms of platform, the same thing. We have encapsulated the whole platform interactions of the library. All the timing functions are encapsulated in the platform namespace. All the error handling solutions are encapsulated in the platform namespace. For example, the allocations, if the user decides to use the section of the API that will allocate memory, it won't allocate memory using malloc. It will allocate memory using platform. In that sense, the user will have the control of where is this memory being allocated, or even, for example, if you want to ensure that the library does not allocate any kind of memory, you can override this method and make it always to return a null pointer, and you can ensure at some point that the library is not using any kind of heap. Well, so this is the SafeDDS architecture that we propose. We also wanted to present some performance measurements in this initial presentation, and we have made a couple of tests. We have measured latency, memory, and CPU usage. With respect to latency, we have created a very basic test that is the very same test that we use with FastDDS. And this is one publisher, one subscriber sending sequential data, and we measure the round trip time, the half of the round trip time. And we have tested this for BSF4, reliable, and interprocess. Because I have not mentioned that, but SafeDDS comes with a built-in intra-process mechanisms that allows local publisher and subscribers to communicate without the need of a transport. Also, the payload that this publisher and subscriber in the latency test sends moves from 16 to 16 Ks. And here we can see the results. We can see the comparison between the pre-release of SafeDDS. Those measurements are from 1 month ago or something like that. But we see that we, in BSF4 UDP, we have the very same results as we can have with FastDDS. In that sense, the interesting thing is that we are more predictable. In that sense, the execution of SafeDDS is more predictable. And this is why the red dots are all together instead of spreading along the 10 to 15 microseconds points. Same thing for reliability. Here we are using DDS reliability QoS, and we find that we have the very same latency results. And finally, the results for intra-process. Here we are comparing with FastDDS intra-process mechanisms, and we find that the results, the latency results communicating entities in the same process is almost bounded by the machine restrictions. All these three tests, all these three results that I have presented have been done using a specific procedure of 40 iteration in the very same machine, sending 10,000 samples per iteration, so they are replicable. Well, those are some conclusions that says that we find that we have the same results, but with a more predictable execution time or communication time or latency. We also have measured memory and CPU usage. We have used the open source iRobot Sierra Nevada scenario that defines some entities, some data size, and some rates for communicating those entities. They propose a graph of nodes and communications. And we have implemented this very same scenario using SafeDDS and using FastDDS. And we have used a tool that they already provide in their GitHub repo, that is this resource usage logger, that allows us to measure the CPU usage and the memory. And here we can see the CPU usage. I have to mention a couple of things here. That is that we are using the default executor of FastDDS, and it uses about 0.5% of the computer CPU. But in the case of SafeDDS, we found that we can modulate this. If we want Safe to be more responsive, we can modify the executor and make it consume more CPU, or we can make it more less responsive in a sense, but accomplishing the communication requirement, of course, and consume less CPU usage. In that sense, you will find that SafeDDS have a default executor already implemented that behaves in the same way that FastDDS executor behaves, but you can tune the execution model of SafeDDS to make your application consume more or less CPU. And this is the most important thing, the memory usage. We have measured the RSS, that is a resident memory usage of a Linux process. And you can see that FastDDS uses more than 20 megabytes of RSS, that is basically a mix of heap, stack, and static memory. And SafeDDS uses less than 5 megabytes. At some point, this result feels weird to us because we know that safe DDS uses much less memory than that. So we measure a empty main program, and we found that the measurement tool, this usage logger, measures almost the very same for an empty main application than for safe DDS. This is why we make some other tests with other kind of scenarios using an STM32 basic discovery with a single publication and single subscription. And we have found that we can embed safe DDS in 30 kilobyte of stack and BSS and about 70 kilobyte of flash. That means that you can use safe DDS in almost every mid-low range MCU that we are used to use. All those STM, all those Cortex M3, M4, M7, even some M0s that are sold by ST Electronics can have enough memory to run a basic application using safe DDS. For this test, we use FreeRTOS and FreeRTOS plus TCP. And also you can see that we follow an approach where there are no dynamic allocations. So we have a 0-byte heap, but I can say that in the fully fledged, fully compliant DDS implementation of safe DDS, you will find that some allocations are required in order to accomplish with the DDS API. And some conclusions. Well, regarding the safe DDS and ROS compatibility, we have been doing tests, and the compatibility is possible in the same way that you can write a fast DDS application that communicates directly with ROS2. You can write a safe DDS application that communicates directly with ROS2. In that sense, the only thing that you have to do is have a compatible type support and writing the name mangling for topic name and type name and all those kind of things that ROS2 makes internally. But it's very easy and very possible to use a safe DDS application along with the ROS2 data space. Regarding platforms, safe DDS is very portable, because we have the whole platform abstractions in the platform namespace. We find that we can run safe DDS in bare metal environments, because the most important thing that the platform namespace provides is the time, and we can implement the time with a time tick, a system tick. So we can run safe DDS in bare metal environment without any kind of RTOS. And regarding the portability, the bare minimum thing that safe DDS needs is a C++ 14 or 11 compliant compiler, and some things of the standard library. Those things of the standard library are basically an array and a couple of byte definitions of how many bits there are in a byte, and those kind of things that are very common and can be overridden from the overwritten from the STD. That's all regarding portability. And regarding execution, I think that this is a very important value proposition of safe DDS, and because we have found that with the concepts of spinning and happening work and all the other methods that we provide in order to move and make the entities to perform the operations and perform tasks, it's very possible to prepare custom environments where the DDS entities behaves well in responding to user requirements in terms of priorities or in terms of threads that will move some data from one side to another, and customize your execution model. And this is something that we have not seen in any DDS implementation. Of course, as I have mentioned, we have been very, very worried to provide like default solutions, because we find that a user that is used to write DDS application will need to have a fully compliant DDS API. So this is why we have default executor and we have default discovery and all the default things. But the important point here is that SafeDDS provide mechanisms for modifying this default behavior very easily and very intuitively. And that's all. Let me know if you have any question.
Hey, Pablo.
Hi.
Thanks for the talk. So can you guys share this slide deck?
I'm not sure. Lara, can you ask internally if we can share
Yes,
this?
I will ask and then I will come back to you, Tomo. Yeah.
Okay,
With
yeah,
the-
no pressure. Yeah,
Okay.
if you can.
In any case, I think that we are gonna put this video in the ROS Discord or something like that.
Okay. That makes
Yes,
sense.
the video will be available.
Okay.
So, any question?
Yeah, thanks a lot for this great work. I have a question. How would be then the if I just want to program ROS2, so how would be the integration path to ROS2?
Okay,
I mean,
we
now you
have,
can natively send, but like in MicroROS, you would have a C
yeah.
language front end, or do you think that the SafeDDS will have just an ARMW adapter, so it can be used directly with any ROS2 application, or what would be missing?
I'm not sure. I should ask internally if we are gonna make an effort on preparing an RMW. But the thing that we have been seeing is that, for example, the clients that are working already with the pre-releases of SafeDDS, they have interactions with ROS2, but they are using DDS APIs because they are in real time, hard real time, critical embedded systems, and they want to have the full control without the abstractions. I think that this is a conversation that we have already had some other times, but we are not sure if we are going to provide a ROS compatible API. Because we think that having a wide protocol compatibility is enough for now.
Mm-hmm. Okay.
Okay, have you tested the code with some additional real-time operating system like RTMS, Nutix, Zephyr, and so on?
We provide. We have a modular platform approach, and we provide the code base with support now for FreeRTOS and POSIX and QNX. We don't have yet support, for example, for Sapphire, but I see that it's very easy to port the platform layer to what Sapphire exposed, because what you need to implement is basically an allocator, a method that provides you a time point, and that's almost all. So porting SafeDDS is not a huge problem. But by default, the code base is provided with support for QNX, POSIX, and FreeRTOS. And also you have options, for example, in the CMake, you have options for building without platform support and providing the platform support from the application side in the very same way that MicroROS does. I guess that we are gonna release publicly the documentation, the user documentation, if I have understood well. And there you will find a lot of information about how all these layers and all these portability methods works and all the things.
Okay, thanks.
Okay, so if there are no more questions, I think we can close the meeting. Thank you very much, Pablo, for the presentation. And for the rest of you, I hope to see you in the next working group. So thank you very much and goodbye.
Thank you very much. Bye.
Thank you.
Bye. Thank you very much.
Bye.
Bye. Thank you.
Thanks a lot. Bye.